All right, folks. Just to go through, we left off last time talking about assumptions of our single sample t-test. Someone tell me when are we using a single sample t-test? Sam? Under what situation would we jump into a single sample test?
When we know like the population information.
What specific information about the population information?
Like standard deviation.
Okay. Okay, if we know a mean and standard deviation of the population, what tests are we using? What's that? Z-test, okay? We know the mean and standard deviation of the population. If we know all the population parameters, we're going to compare our novel, or our sample from presumably a novel population. We'll just compare that against a Z-test. When do we switch over and use a t-test?
When we don't know the population.
When we don't know the population standard deviation. When we have a population mean, when we have some reference point, right? We know in the general population, this is the average value on some outcome, right? What we have is a sample drawn from a specific population, and what we're trying to determine is whether or not we have sufficient evidence to draw a conclusion, or to make a conclusion that whatever specific population, or special population I've selected my sample from, that the mean value of that population is different from some reference population, okay? And so for our single sample t-test, some basic assumptions that we need to have in order to make any inferences that we draw from our hypothesis test valid. We need to make sure that we are working with an outcome that's continuous, okay? One of the things, does anybody get nervous or terrified that at some point they have to decide what analyses to do, but they won't know what analysis to choose? Show of hands if that terrifies you, okay? Thing that you need to do is figure out what are my independent variables or my input variables, what are my outcome variable or variables, determine the number of your inputs and your outputs, determine the level of measurement of your inputs and outputs, and at that point you pretty much narrowed yourself down probably a handful of different tests, okay? For a t-test, we have, how many IVs do we have with a single sample t-test? One, right, which is just really sort of our population, and how many outcomes do we have? One. And in this case, our outcome is something that's continuous or that we can at least treat as continuous. Our outcome variables in psychology are very, very often ordinal scales, right? Things that sort of are ranked on. And they're not true continuous scales. Stephanie, why are they not true continuous scales?
They usually have like 5 options, and you can choose something. You can't choose 2 different options. You have to choose.
Okay, so we're choosing ordinal. There's no real way to get right in the middle of things. Okay, so that's one thing. What's the other thing that prevents most of our scales from being true continuous scales?
Just me
in
general. Okay. I'm not sure.
What about, so we've got ordinal things, and so there's no in between that we can have, right? Like on a 0 to 5 Likert scale, you can't just choose 1.5 because you feel like it. Right? What's the other thing that prevents these scales from being true continuous scales? Sam, do you know?
Is it depending on what you're trying to measure?
Well, it kind of depends. But what about the measurement prevents those scales from being true continuous scales?
Well, I was going to say sometimes you can't like divide things like people.
Okay, and so that gets back into some of the stuff Stephanie was saying, that they're really sort of distinct units, right? Remember that with continuous scale, we have to have equal intervals between all of our units, right? So we pretend that if I'm having you rate 0 to 10 on a happiness scale, that the amount of the increase in happiness from 1 to 2 is the same from 2 to 3 and 3 to 4, 4 to 5. Just like if you're 5'8" and you're the same amount shorter than someone who's 5'10" as someone 5'10" is from 6 foot tall, right? But is that an actual property of the scales that we use? No, right? At best, we can say on average, a score of 5 is going to be bigger than a score of 4 in general, right? But if Angeline writes a 5, her 5 might be a very different 5 than Lauren's 5. I don't know, right? So it's important to be thinking about these levels of measurement consequences. Again, that's something we talked about in our very first lecture, but wanting you guys to keep these things in your mind. So, but for our single sample t-test, we've got an outcome variable that's either continuous or that we'll treat as continuous. Rule of thumb, generally thinking ordinal scale of 5 or more values. And that's a really lower bound minimum, right? If you have any less than 5 values on that, it starts to become hard to treat this or pretend that this is something that approximates a continuous scale. We have to have our observations independent. What does this mean? This isn't something we can test statistically, but what are we talking about if we're talking about independent observations, Morgan?
That they're not being, like, the participants aren't being used again for a later sample, like in repeated measures would be,
Okay.
or like that they're not connected in any way.
Exactly, right? So your score is not in any way impacted by Alex's score or Candace's score. Everybody's scores are independent of one another, okay? And then this is the big one that we often start to go through and screen. Statistically we say that our distribution of sample means for the population should be normal. Rosie, tell me what this is about.
So you mean what?
What are we saying? If I'm saying, in order for this test to be valid, I'm assuming a normality in the distribution of sample means.
So this means that if we take a sample from a population for repeatedly for a number of large times, the mean that we get for each sample, so the more number of sample we take, the mean will move towards will be approximately equal to the mean of the reference population. So the graph or the curve that we get will be approximately normalized, will be a normal distribution.
Perfect. And so technically, from a technical standpoint, are we concerned as much with the distribution of the scores in our sample? From a technical standpoint here. So we've got our distribution of sample means, and then we've got the distribution of scores that we see in our individual sample. How concerned are we with the distribution of scores that we're seeing in our sample?
I think it's important to us that the distribution of scores.
Okay, so we are. It's relevant. We want to look at it, but let's say we get a distribution of scores that have some level of skew to them. Does that mean we can't do our t-test?
I think we can do the t-test.
Why is that?
So if the data is skewed, we can determine.
Someone help anybody?
Well, the sample doesn't have to be normal for the distribution to be normal.
Perfect. Okay. And this is such an important concept here. And Rajiv, you're circling the landing pad there. You're getting around it, right? The observed scores, the observed scores that we have, there's no assumption that those are normal. What we're assuming is that, let's say I have a sample of 20 people or 30 people. Let's say 30 people, right? And my observed scores are pretty skewed, right? Technically, on our means-based tests, our assumptions aren't about the observed scores that we're seeing. Our assumption is about the distribution of sample means, right? And so if I can reasonably expect over an infinite number of sampling of sample size 30, that even that skewed distribution will approach normality in the distribution of sample means, I technically haven't violated my assumptions, okay? So, because remember, under what two conditions does our distribution of sample means start to approximate normality, Katie?
If the sample size is 30 or larger.
Okay, and roughly, so as our sample size gets bigger, right? And then what else?
If it's normally distributed.
Right. If we're measuring something that has a normal distribution, cool, our distribution of sample means very quickly becomes normal. But even if we're measuring or testing something or looking at something that doesn't have a normal distribution in the population, something that kind of has a skewed distribution, things like aggression and substance use or other types of traits that are relatively uncommon but occur at varying frequencies in the population, as long as we have a reasonable sample size, and again, went through a demonstration kind of empirically and showed you like that, yeah, as you start to build a distribution of sample means off of a population that even is very skewed, and even if you look at even the individual samples is very skewed, still the distribution population means starts to become normal, okay? Now, this isn't to say that you can run a t-test on whatever data has to come up, whatever things come up. We can get stuff that starts to become problematic, particularly if we've got outliers, right? If we've got a wonky distribution, we've got scores hanging way out on the extremes, either the upper or lower end. Why is this problematic for a means-based test? Angela, what do you think?
Because it can skew the mean and pull, outliers can like pull the mean in
There
that
we
direction.
go, right? Outliers are always going to pull the mean towards them, right? They're like they're intense gravitational entities that are just pulling that out, right? And if we have small samples or extremely outliers that are way, way out there, what that does, we're running these tests on mean values, right? And if we've got one case in the sample or two cases in the sample that are dragging that mean way out one way or the other, it's reasonable to suspect that our mean value isn't actually representative of the population. It's been adversely impacted, right? And so although outliers aren't a formal assumption, it's something we always want to go through and take a look at, okay? So we had gone through and screened our single sample stuff. We had gone through, if you remember, we went through, asked for our descriptive statistics, took a look at the min and the max to make sure that our values were plausible. We didn't have anything way out of bounds, right? If we've got a scale that runs from 0 to 20, and we have this score of 25 in there, we know that something's gone wrong. Always, always, always want to make sure that you have reasonable values. Taking a look at your sample size, making sure that the number of people in your set are the number of people you think you're working with. Looking at the skew and kurtosis values. These are nice. These are indices that we can use to start to say, yeah, these data are, look like they're approximating normality, or probably a better way to phrase this is that these data suggest that our distribution isn't severely non-normal, right? It would be hard to call something with a kurtosis value of 4 normal or approaching normality, but we can say that it is consistent with a distribution that isn't severely non-normal, right? Probably a better way to phrase that. So we took a look at that, but then always, always, always want to look at things graphically. Created some histograms. Our histogram of our distribution of scores looks not too bad. Everything's kind of symmetrical, doing what we should. For 27 scores, that's not a bad distribution. We also looked at box and whisker plots. Remember, our box and whisker plots are median-based statistics, right? We're talking about percentile scores here, the 25th percentile, the 50th percentile. What's the 50th percentile?
Median.
Yep, median. 50th percentile is the median. 75th percentile, we've got our whiskers that go out to the value that's 1.5 times the interquartile range farthest out. Values extending out beyond that, individually marked as extreme values. Do not, please do not just identify something as an outlier because it shows up as a circle on a box plot. I want you to be thinking about what's going into some of this stuff. So we went through, took a look at that, and then we ran our z-scores for our outcomes, looking at values. And how are we interpreting z-scores, Alex? So when we go through and we went through and ran z-scores, we had told SPSS to create a z-score for every single observation in our set. And then we went through and we took a look and we're trying to see values that might indicate an extreme score. How do we, what's the interpretation of a z-score? If I say, I found, in this example, we've got at the low end a z-score of negative 1.85. What's the practical interpretation of that z-score?
Z-score of 1.5 is 1.85 standard deviations away from the mean.
In which direction? Okay, if it's negative. If it's a
Oh,
negative z-
sorry.
below,
Yeah.
right? So we would say literally that this is a score, the lowest score in this distribution, it's falling, approaching 2 standard deviations below the mean, exactly 1.85 standard deviations below the mean. Again, that's far on the margins, but it's not probably something we're gonna get too worked up about, right? So taking all this together, and what did we end up concluding based on our screening of these data? Anybody remember? Sam, you remember what we concluded based on our screening that we closed out with?
I don't remember.
Based on what we've gone through, and looking at our assumptions, what would we probably assume based on our, this screening?
I don't know where to find that output.
Okay, we got, so did people bring, you guys have the handouts stuff that we posted on Wild Courses? Does nobody have these? Okay, if you look under, yeah, I posted these last week. These are, under our handouts, you should see a whole bunch of stuff that talks about screening and things like that. However you want to work with those, I prefer to have printed out copies, but if you are fine working with them electronically, that's fine too. These are going to be important for seeing where we're at and how we're working through this stuff. So based on the screening that we went through, do we have major concerns with our data in terms of running a single sample t-test, Angeline? No, we don't, right? Things are looking pretty good with this. All right, so what we're going to do now is we're going to grab our set and we're going to switch over to our handout here that has single sample t-test, just the actual test. And this ends up being pretty easy and straightforward, okay? What we've got here is a hypothetical situation, again, if you're looking at the handout here, where we've got scores from a bunch of individuals who have come in and seeking treatment for anxiety following a serious car accident. And what percentage of these people meet criteria for PTSD? You remember? Based on our data, that PTSD final variable on there? All of them, right? So we've got a group of individuals who are meeting, based on our study, would meet diagnostic criteria for PTSD. And so maybe what we do is we want to get a sense for whether or not our sample and the people who we've diagnosed with PTSD have symptom levels that are consistent with some, let's say, normative reference. Now this is not a great normative reference because it's not necessarily a population, but let's just pretend these are normative values, okay? And so you'll see in the variables box here, we have our participant ID, we have our diagnostic variable, which those are all ones, so that's not a variable, it's a constant. And then we've got our CAPS total. This is our continuous, and we find, and what we're gonna test against is we say that normative scores in the population based on this Coffey et al. 2006 paper, individuals who present, who've been exposed to trauma but don't meet diagnostic criteria for PTSD, their average score is 24.7 with a standard deviation of 18.7. People who do meet diagnostic criteria for PTSD, again, if we're using this for some reason, this is the criteria, this is what we're basing things on. People with PTSD have a CAP score of 70.1 with a standard deviation of 17.6. Okay, and so what if our question is, we've got a group of 27 individuals who we say meet criteria for PTSD. And we want to make sure, Stephanie, how would we expect these individuals to score relative to the population of individuals without PTSD? We should be higher, right? And if they're not higher, that's kind of a problem. It suggests that maybe there's something funky with our assessment procedures, right? If our PTSD sample doesn't have we don't have evidence that the mean value in that population is different from the population of individuals without PTSD, right? Based on our criterion score. And so what we can do with our independent sample, or with our single sample t-test, is we can test that, okay? So what we're gonna do, because we've screened this already, right, and we know that we can do this without concern, we're gonna go to Analyze. We're gonna go to Compare Means, and we're gonna go to One Sample t-test. Click on that. Now it's gonna ask you for your test variables. You can put in whatever variables in here you wanna test. Are these your inputs or your outputs? These are gonna be your outputs, all right? These are gonna be your dependent variables. That's all right, Alex. I like that you're taking chances. It makes me happy, all right? So we go take our total CAP score, drop that in. But if we wanted to test other scores on against something, we could drop those in as well, okay? And so then we've got this test value. What do you think we put in this test value?
70.
Okay. What are we? What's the reference population that we identified for this first example? Yeah, and why is that? Talk with me through the rationale.
Because we're comparing to see if it's different from like the people without PTSD.
Exactly. So these are still people who have been through something, right? But they don't meet criteria for PTSD. And what we want to see is whether or not we have sufficient evidence to make the claim that the people that we've assessed have a higher mean average, or have a higher average score on this CAPS measure than people who, some reference group that doesn't have PTSD, okay? And so what we're gonna do is we're gonna put in our reference value here for people without PTSD, 24.7, okay? Then we're gonna go up and we're gonna hit options. And what we can do here, depending on, and what SPSS is gonna do, we're gonna love SPSS for this. It's gonna calculate confidence intervals for you, which is nice. It saves you some time. P.S. As we move through this, there will be times when, one, you can't use SPSS because you don't have the raw data, or two, I tell you not to use SPSS. I tell you to do things by hand. But if I don't tell you that you need to do them by hand, or that use the tools available to you. Like every year I have people cranking stuff out longhand when I was like, no, you didn't need to do that. Just run it through the computer. It's going to save yourself time and effort, okay? So just as a heads up. But if we wanted to change and let's say calculate 99% confidence intervals, 90% confidence intervals, this options case is where we would do that, okay? And so we won't do that though. So we just go ahead and hit paste. And here is our syntax. Easy, not too difficult. We go through, we run this. Everything's pretty easy, pretty straightforward, okay? We see within this output, and when you get output, you should be able to go through and identify every single piece of this and be able to tell me what it means. That doesn't mean we'll always use stuff. SPSS sometimes gives us stuff that's not worth paying too much attention to, but I still want you to know what it is and whether or not you need to pay attention to it, and not why you need to pay attention to it. Anybody ever have a class where you say, what's that? And they're like, don't worry about that, right? We're doing graduate level statistics here. I want you to know conceptually what these things are, and if you're going to ignore it, know why you're ignoring it. Here, we start out with just a summary. We've got our total number of scores, our mean of our sample, our standard deviation of our sample, and then the standard error of the mean, okay? Can someone tell me how they calculated the standard error of the mean, Rajiv?
So standard error is equal to standard deviation divided by the number of square root of number.
Perfect, yeah. And if you can go through and you can calculate this, verify your for yourself, right? If we take the standard deviation divided by the square root of 27, that's what we're gonna get, right? And so it's nice to be able to go through and recognize these pieces because later on you're gonna have to do some hand calculations, and it's nice to be able to pull stuff from your output and just plug that in, as opposed to running into the possibility of making an error as you're going through and calculating standard errors by hand and things along those lines, okay? So we've got our summary statistics. Always go up through and make sure that if this says 25, you know something's gone wrong, right? Because that's not the number of people I should have in my sample, right? Making sure everything squares up, and then go down. This is our one sample t-test. Our test value, our reference value, 24.7, corresponding to our reference population of individuals who have been in accidents but don't meet criteria for PTSD. Here's our t-score. How do we arrive at that t-score? Sam?
The sample minus the population.
Perfect. Almost. In order to get a test statistic, what do we always divide by? Standard error, right? Remember, our test ratios are almost always going to be, this is how much different we saw versus this is how much difference we would expect just from random sampling stuff, because that's what our standard error is, right? And so if we take the difference between 62 and 24.7, whatever that difference is, it's 37.3. And divided by 2.598, we're going to get our test statistic of this, right? So again, putting this together so these just aren't magical numbers that come out of nowhere. So you can take a look and say, does this make sense, right? Anytime you get a t-value of 14, you should probably make sure that all makes sense, right? That's a very, very large test statistic, but in this case, it makes a lot of sense, right? So we've got our t-statistic, our degrees of freedom. Morgan, can you tell me where I got this degrees of freedom in 26?
N minus 1.
N-1, perfect. This is our p-value. Do not tell me p equals 0. P is never equal to 0. We say p less than 0.001 in terms of your reporting. Here's our mean difference, and then here is our confidence interval for the difference. All right, now this is, in some of our examples, we've been calculating confidence intervals around the mean value. Here, SPSS is creating confidence interval around the difference, okay? It's essentially the same thing. Katie, what should I not see in this confidence interval if I'm hoping to find a reliable effect? Yeah, right. And so, well, the population mean, if I'm just calculating the confidence interval around my mean value. If we're calculating the confidence interval of the difference between my score and the population or the reference value, what should I hope to not see in that interval? Okay, not quite. So I mean, I'm probably not answering this question. 7, can you have 5 here? 0, right? Because as opposed to here's what we've been doing up to this point, we say, okay, we've got a mean value of 62, and then we're calculating confidence interval and saying, so our sample, our best estimate of the mean CAP score in the population of individuals with PTSD is 62 with a lower bound of this or that, right? What we've got here is a little bit different. What we've done, we've said, well, this is the difference, the mean difference between what our best guess of our population mean is relative to the reference point. So we're saying here that based on our data, we expect a difference in the population. Our accident survivors with PTSD to be on average 37.3 points higher on the CAPS than the population of individuals without PTSD, okay? And the upper and lower bound for that difference, we would say, based on our data, we would expect reasonable difference between our population of individuals with PTSD versus the population without, a lower bound difference of about 32 points above, maybe all the way up to 42.5 points above, okay? An important distinction to make, right? And this is why it's important to think about your numbers and what makes sense, right? Would this, Angeline, be a reasonable 95% confidence interval for the mean value in this sample?
Yes.
For the mean value. If I said, here's a confidence interval around mean score,
Oh, no.
why not?
Because it's outside. I mean, that is outside.
It's outside, mean value is outside. 62 is not in here,
Yeah.
right? So already we know that this can't be a confidence interval around the mean value. It's confidence interval around the difference, okay? So making sure that you're going through and understanding what you're getting here, okay? So we've got our test statistic, we've got our confidence interval. What's maybe the other thing that we might want to get out of this? In order to do a good job of communicating what we have here. An effect size, absolutely, right? And this is nice because we can just start pulling values off of our output. So if we're going to calculate D in this case, D is going to be the difference between, well, we've got our mean minus our reference value over standard deviation, right? So here, what's the difference between our sample mean and our reference value? 37.3, right? You just look at the thing, and this is where it starts to become nice. You can just look, I mean, you can calculate it by hand, that's easy enough, but it's just sitting there in the middle of the output, so you can just pour it there. And what about our standard deviation? What's our standard deviation? Katie?
The standard deviation is 13.49.
What's that?
13.499.
13.499, all right. And what do we get in terms of our effect size here? What is it?
2.76.
2.76. 2.76 what?
3.
Okay, 2.76.
Yeah.
All right. And Alex, can you give me an interpretation of that effect size? Remember when you gave me that glorious interpretation of Z scores? Do the same thing except replace Z score with effect size.
Oh, so it is the standard deviation, so it's 2.76 away from the mean.
Exactly, okay. Interpreting means-based effect size is not difficult. They're basically the equivalent of interpret the same way you would interpret Z scores. What we would say here is say based on the data that we've collected here, looks like individuals with PTSD in our sample are scoring about 2.76 standard deviations above the mean of the population, of the reference population. Is that a big effect or a small effect? That's a massive effect. That's a massive, massive effect, right? But this is nice, right? So you can say, oh, our individuals with PTSD are scoring higher than individuals without PTSD on this measure, right? Which says, yeah, you can say it's reliable. But here what you can say, between your confidence interval, you can say we're expecting individuals with PTSD to score anywhere from 32 to 42.5 points higher on the CAPS than individuals without PTSD. This difference corresponds to about 2 3/4 of a standard deviation above the mean of the reference value. We're not just saying that, yes, this is statistically reliable. This is a big, big, big difference. Okay? Remember, our effect sizes are giving us an estimate of the magnitude of the effect in the population, irrespective of what our sample size is. Okay? And so here, we've got pretty much everything, at least that we've talked about getting to this point. We've got a confidence interval that we can interpret and start to make some conclusions based on that. We've calculated an effect size that's super exciting. If you get an effect size of 2.75, should be excited about that, right? And then we've run our hypothesis test. But by the time we use our hypothesis test, there's really not a lot of new information there to be had, right? Because everything that we would get, the only thing we're really getting is a test statistic and a p-value that we can report to make mom happy, right? But aside from that, we've got everything that we need, okay? Questions on any of this? All right, so now, just for the hey-ho heck of it, what else might we want to test, given this scenario that we've put together? So we've established that individuals from the population that we're drawing from have a reliably higher scores on the CAPS than a reference population without PTSD. What else, based on this measure, might we want to take a look at?
How our participants differ from people with PTSD?
Right, right. And now this is a little bit tricky, right? Because how would we hope our sample to turn out relative to the population of individuals with PTSD, our reference population? The same, right? And can we make strong, and so what, if they're the same, what would that correspond to in terms of our hypothesis test? I will punch you. We don't say accept the null, right? We fail to reject the null, right? If we fail to reject the null, we're saying that we don't. What is our interpretation of failing to reject the null?
That we didn't find a significant difference.
Okay, that we didn't find a significant difference, and what does that mean?
That it felt like he wasn't drawn from a population. I have the word there, but I can't get them out.
No, I like what you're saying, but let's simplify it. What is the interpretation of a null effect? Right? We're not saying that there's an effect or there's not an effect. We're just saying that we don't have enough data to claim an effect. Right? We don't have sufficient evidence to claim an effect based on these data. We're not saying they're the same. We're just saying that we don't have enough evidence to say that they're different. Right? And this is a tricky thing, and I want you guys all to remember this, because if I want to run a test where I'm hypothesizing the null, it's problematic because even if I fail to reject the null, I still can't conclude that my sample is the same as the reference sample. I'm just saying I don't have enough evidence to suggest that my sample is different from the reference sample. And so this next test that we'll run is wonky in terms of theoretically, right? We can say we don't have evidence to suggest that our sample is reliably different than the other sample, but again, basically, we're making a conclusion based on a null result, which you always have to be very, very careful about, okay? But, that's nice. Angela, I'm sorry, I'm not gonna punch you out there. I forget, right? All of a sudden I'm gonna get a grievance, right? We have you on YouTube threatening to punch a student. All right, so this is where your syntax comes in handy. We could run through menus and run change in this second statement, Rajiv.
The test value?
What's that?
The test value?
I'm sorry, one more time?
The test value, like 24.
The test value, yeah. I mean, this is nice, right? Instead of having to run through, we'll just go through and put in 70.1, right? And you'll notice, and you'll start to see as you start to become more familiar and comfortable with these syntax statements that you don't have, particularly if we're running different regression models and stuff like that. It's kind of tiresome to go back up through and run everything through through your pull down menu. You can just go through and say, all right, I did this once, now I need to want to do it with another variable, just cut and paste there. And so if we go through and we run this, what are we seeing here? What do you think, Stephanie?
That our sample mean is lower
Okay.
than the population mean.
Right. And so what we would and how are you making that? How are you drawing that conclusion?
Well, for one, the mean difference, also the 95% confidence interval of the
Uh-huh.
difference does not include zero.
Uh-huh.
And the difference between the groups is statistically significant.
Exactly, right? So it looks like based on these data, our population from which we're drawing from, right, is on average about 8 points lower on the caps than our reference population, right? And we find that if we look at the 95% confidence interval, this is our point estimate. Our best guess is that the mean of our hypothetical population is running about 8 points below what our reference population is. And based on our data, that difference could be anywhere from about 2.76 points to 13, close to 13.5 points lower than our reference value. If we go through and calculate our effect size here, we got D equal to 8.1 over 13.499. What's our effect size?
.60.
0.60?
Yeah.
Okay. Anybody remember off the top of their head Cohen's benchmarks? It was moderate. Yeah, we would put this a moderate effect, right? Morgan, can you give me a practical interpretation of this effect size here?
That our sample is scoring on average 0.6 standard deviations below the reference population.
Yeah, right. So we're about, based on our data, it looks like we're scoring about 0.6 of a standard deviation below, 0.6 of a standard deviation below our reference value, right? And that's consistent with a moderate effect. And so, based on these data, we're certainly doing our population that we're drawing people from are definitely scoring higher than the reference population without PTSD. But it looks like we're also scoring moderately lower in terms of post-traumatic symptoms than our reference population, at least based on this, right? And so again, this is a fun, ambiguous situation where we have to come up with some thing, right? It's one thing to just say, yep, it's higher, but it's also lower. But then bringing that together and start talking about what's maybe going on in terms of how do we interpret this, how do we put it together and draw some sort of meaningful conclusion that has some sort of interesting relation to the stuff that we're doing, right? So I don't know if this is my data, I was like, oh, well, it looks like we're certainly capturing individuals with PTSD, right? Like we're not scoring so low that we're not actually, so that our people are scoring in the range of people without PTSD. But it looks like we're scoring a little bit lower than people in this reference population in terms of our the individuals with PTSD or do have meet criteria for diagnosis. And I don't know, that could be, what might account for this? I can think of a couple of things. And not our sample size necessarily, right? Because our sample size, if we didn't find a reliable difference, we might say, well, maybe we have low power because our sample size is low. And again, this is kind of tough. Rajiv, I'll exclude you out of this because you're not a psychologist. But if you're thinking about, hey, we're running a clinical study and we're bringing people in and we're running assessments, and it's a clinician-based assessment, right? So it's not objective, you're just writing things down, like you're literally scoring and rating people's symptom severity. What are two possible things that might be going on with these data? What do you think, Steph?
Well, what I was thinking, I don't know if it's compatible with what you just asked, but depends on like where we recruited them from. Like if we recruited them from the treatment facility, then maybe they may have received treatment already.
Exactly.
So
So maybe we're working with a different population, right? Maybe, and by definition, our population is probably going to be different than the one in some respects from the one that we're using as our reference, because it's not really a reference population. But so it's possible that maybe we just have a slightly less severe population of individuals that we're sampling from. What's the other maybe less comfortable conclusion that we might draw? If we're assuming our population values are infallible and whoever's doing that, those assessments are doing them 100% correctly.
and we're assuming that
That Coffee et al. Are administering this test perfectly and exactly how it should be administered. Yeah, right. Then maybe we're running a little lean in terms of our ratings of stuff, right? Maybe as we're going through and coding things, maybe we might be trained, right? And if we have inter-rater reliabilities, we might say, oh, we're all on kind of the same page, but, right, if here's the center, right, we're close, but we're just all maybe a little bit off over here, right? And so I don't know, right? But these are the types of things we want to talk about, so how do we start to account for this type of stuff, right? And this might be good because you're saying like, well, we're clearly around where we were supposed to be, and if our inter-rater reliabilities are good, it looks like we're all pretty much doing the same thing, but maybe as a group, we're just a little left of center here. Or maybe we're working with a different population. I don't know, one of the two. But these are the types of things we're wanting to think about in terms of accounting for, and it's sort of artificial with data that you're not familiar with and in a topic area that you don't care about. But these are the types of things that make for good discussion sections that are interesting to read, and crappy discussion sections that don't tell me anything I didn't already know from reading the results, right? I don't need you in your discussion section to just tell me that you didn't find anything, or that I found things for these two variables, because I know that, I read that piece of it. Tell me what this means, tell me what the implications are, that type of thing, okay? And so hopefully by twisting your arm and threatening physical violence on you throughout the course of the semester will start to get you in a space where you're automatically starting to think, okay, what are the implications? What does this stuff mean? Okay. Any questions about our single sample T? Okay, cool. So, yes, here we go. Again, inside my brain, like how I'm reading Wilkinson and things like that, these are the images that are coming up for me. Always wanting to go through and make sure that we're reasonable in terms of our assumptions, right? Here's a write-up. Again, this is a write-up, an idea for how I might go about doing this, having done this for a while. If I were to make a write-up for this assignment. You can see that this is kind of involved, right? But as you're going through and reading this, notice what I'm trying to do here, trying to make sure that this is packed with information that's gonna let me know that you're understanding kind of what's going on here, right? So we're talking about our hypotheses, right? And providing information, what we're actually testing. Here, we're talking about our screening, kind of putting some thoughts together here. Here, we're talking about the results. We're providing means, standard deviations. We're providing an effect size and giving a meaningful interpretation of that effect size. Talking about our confidence intervals, providing a meaningful interpretation of confidence intervals. Then we talk about our test, making our assumptions or our conclusions based on this. kind of to tie this all together to provide Candace and I with a demonstration that you have your bases covered, you're making a strong interpretation based on your data, and you're kind of pulling all this stuff together, okay? Now, please do not copy and paste and use this. This is mine, this is an example, this is not for you to use as a template, but this should, I would encourage you to go through and take a look at this as a general kind of framework and get an idea for how we want to go through this. I can tell you, like, even without talking with your advisors, if your advisor gives you something and says, here, look at this, whatever you produce should probably kind of look like that. It should be your best effort to recreate what's going on in thematically or whatever. Sometimes we think, oh, I might have a more better creative way to do that. Maybe you do, you probably don't. It's probably going to be, it's probably going to be more difficult to work through, right? Talk with your advisor if you feel like you have a more creative way to do it. But in some ways, scientific writing can be formulaic, particularly when we're talking about reporting results and things along those lines. Right? It's always disappointing to give someone an example, say, here's an example, kind of like this, and then get something that's completely different. And then we have to think, it wasn't for my health that I gave that to you. I kind of was, so that like when I go through and read, it helps me not be stressed, because now I have to tell you everything that I was hoping that you would get from this template, but whatever. So, but these are the types of things that in a really strong interpretation that I would be looking for. Right? We've got figures, we've got everything integrated in to something that is demonstrating that you understand the working pieces of all this, okay? Now, that's really long, right? For something like a publication, it's gonna be much shorter, right? Our journal editors just won't tolerate us going on and on and on about things, but that doesn't mean that we shouldn't be trying to incorporate stuff to the best of our ability. This would just be an example of if we were writing this up for publication or something like that, how we might kind of start to condense this down to something that might be more appropriate for a scientific journal versus 5600 assignment, okay, or 5060 assignment, okay. So go through, take a look at those. Again, please don't cut and paste. I'll actually get really aggravated if you cut and paste and just punch stuff in, but in your own words, try and sort of, just to give you an example for what we're looking for, okay? Also, right, as you're going through, and anytime you you explode something out of SPSS, right, as a result, always go through and take a look at that and say, does this make sense? Is this a reasonable thing, right? I don't know how often in papers that I'm reviewing or projects or things along those lines, in fact, we found an effect size of 50. But I don't think you did, because that doesn't make sense, right? So always when you're going through, and hopefully what you're getting, like we're getting like deep into the weeds in terms of understanding the mechanics of this, right? You all are going to be technicians and understanding, you know, right? What happens a lot of times, Angeline's car's broke down, right? You take it to a mechanic, you don't want to say, yeah, it doesn't work. It's not running, but yeah, I know it's not running. I want you to tell me what's wrong with it, right? That's the level at which I want you guys to be working on this stuff, so you can go through, get into the guts and say, okay, this is probably where things are going wrong. So always, always, always take a look and say, does this make sense? And this is where there's practical interpretation. As soon as you have to voice out words, say, oh, this score is 7 standard deviations below the mean. That doesn't seem to make sense to me. Let me go back through and see what's going on with stuff, right? It's just going to be incredibly helpful for making silly errors and stuff like that, okay? All right, so up to this point, good stuff. We've got a new tool in our belt. We've transitioned from Z into T, but still our single sample Z and our Ts are still requiring more information that we typically will have within before we can run a test. Basically, through our single sample t-test is requiring us to know some population value or some reference value, and oftentimes we don't have that, right? What we're often faced with is wanting to compare means from 2 or more different samples with an unknown mean, unknown population, unknown population mean, unknown population variance, okay? I want to know if population B is different than population C. but I don't know what the population values are for those two groups, but I'd still like to see if they're different on some dimension. This is where we get into our independent sample t-test. Okay? With our independent sample t, what we're looking for is reliable difference between two population means. Okay? Not samples. All right? I don't need to run the t-test to know whether or not sample A is different than sample B. Alex, how do I tell if sample A is different than sample B? Yeah. Look at the means, right? I don't need a statistical test to say sample A has a mean of 30, sample B has a mean of 32. Is 30 the same as 32? It's not, right? I don't need a statistical test to say that those two things are different. What I'm interested is trying to make an inference about whether or not the population from which sample A was drawn is reliably different than the population from which sample B is drawn, okay? And so what we want to do, though, is because we don't know the mean of the standard deviation of our two populations, what we have to do is we draw samples. Hopefully a good sample, hopefully a large sample, hopefully a representative sample from these populations. Then we run our test to see, is the difference that we see between our two sample means, does that exceed what we would expect based on just sampling variance if we were to be drawing two samples with the same, two samples from populations with the same mean? And if we do, if we're seeing a difference that's a lot more than we would expect just based on random variance or random error, then we say, yeah, we probably have evidence to conclude that these populations, or these two samples come from populations with different means. If it's not, then we say, well, I don't know, we can't say that there is or there isn't, we just don't, we're gonna say we don't have enough evidence to say that there is an effect. Okay. So again, population A, population B, don't know these, but what we're going to do is we're going to draw some samples and test those samples there. Okay? So, for our independent sample test, our null hypotheses, population 1 minus the mean of population 2 is equal to 0. Okay? We can also write this if we wanted to. We could say population 1 equals population 2, right? But my preference would be for you to use this, because this is what we're actually testing, right? We're not testing, I mean, we're indirectly testing that population 1 is equal to population 2, but we're doing that because what we're really doing is taking a look at whether or not our difference value between these two things are 0, right? This is the numerical equivalent. So if you would provide these out in statistical notation like this, the difference between the population means is 0. What's implied here is that scores will likely be drawn from populations having equal means, or probably with similar means, right? But our alternative hypothesis is mean 1 minus mean 2 is not equal to 0. For our two-tailed test, we're saying that the difference in population means is some non-zero value, right? Our observed scores are unlikely to have occurred if the means of the respective populations were equal, right? Essentially, I think, again, going back to what we're actually getting in our hypotheses test, if population 1 has a mean that's equal to population 2, it's very unlikely that we would select two samples randomly from those populations that would deviate from each other to this degree. Okay? Now, the one thing I'll say, when you're going through and you're making your interpretations, please don't tell me that the difference in population means is some non-zero value. Why am I going to be upset with that? If you run your statistical test and you reject the null hypotheses, and you say, this means that the difference in population means is some non-zero value, why might I be unsatisfied with that in terms of practical interpretation? What do you think, Steph?
Because you're not providing information about which mean is higher.
Yeah. And this is a silly mistake. I know you're not trying to be evasive or withhold information from me, right? But it's just one of these things that it was like, oh, that means that the population means are different, which is true, but it's not helpful for me because what I want to know, what does that look like? Does X get bigger? Does X get bigger? Does Y get bigger? Is A bigger than B bigger than A? Make sure that you're being specific on in your interpretations. Okay. Again, what we're testing with our independent sample t-test is the difference in scores between the two samples sufficiently large to conclude that they were drawn from populations with different means. Okay. So again, But thinking in this vein, forcing you in, when I ask you to say, state in words what the null hypothesis is, forcing you to tell me what these populations are, and not just saying population, like identify what the populations are that we're actually looking at, is gonna help you start thinking about and place this within the frame of what we're actually doing and not what's more than just rote brainless, like, yep, they're different p-values, that type of thing. All right, assumptions of our independent sample t-test. Formal assumptions, outcome is continuous. No news there, right? We already knew that. If we're thinking about under what conditions are we looking at an independent sample t-test? How many independent variables do we have, Sam, in an independent sample t-test? How many IVs? One, perfect, there you go. Why is it only one? So I want to determine whether men and women are different in height, right? So I've got a continuous outcome, height, and I've got one outcome variable, or one input. What's my IV in this case? Okay, so I want to know if men and women are different in height. I've got my outcome. Outcome is height. What's my independent variable? Yeah. Gender, physical sex, whatever, however we want to categorize it. How many levels do we have to this variable? Two, right? So, and this can be tricky, right? We just have one IV, right? The IV is gender, physical sex, however we want to do that. It's got two levels, right? So if we have one, and what is the level of measurement of our IV? Sam? Level of measurement? Of our independent variable. Anybody help out? What is it? No, not of our independent variable. Our independent variable is what type of variable? Categorical. It's a nominal scale, right? It's a dichotomous variable, right? We're looking at the relation of a dichotomous variable with a continuous outcome. This is a t-test, right? Well, there's other things we can do, but for the purposes of what we're doing right now, we'll look at this with a t-test, okay? But again, as we're starting to identify what type of test should I be using, first, how many IVs do I have and what's the level of measurement? What's the DVs? How many of those do I have? What's the level of measurement? The stuff that we'll do this year, or for most of this whole year, you're only gonna have one dependent variable for the most part. But how many independent variables do I have? What's the level of measurement? And then all of a sudden that's gonna focus me into what type of test I'm gonna be using. So with our independent sample t-test, one dichotomous variable, that will be nominal for the most part. Outcome variable is continuous. Observations in each sample are independent. That means that if I have group A who get instruction and group B that get a different type of instruction, that everybody's scores are independent of one another, and we don't have any crossover there. We again expect, and this is important to recognize, the distribution of sample means for each population is normal, okay? In terms of screening, what does this mean we're gonna have to probably do? Can we look at will we be able to look at our distribution of scores all together? What do you think, Steph?
Look at the distribution of each group.
In each group, right? We're gonna have to separate these out, right? Because what we wanna do is make sure that we're sufficiently comfortable claiming that the distribution of sample means for group A approximates normality, distribution of sample means for group 2 approximates normality. So when we're running our screening, we're gonna have to split these up. We're gonna have to make sure we're doing that different. We'll show how to do that in SPSS. But here's the new assumption. Homogeneity of variance. Okay, homogeneity of variance is the assumption that the variance in both populations is equal. Okay? We're saying that hypothetical population out there in the universe, right? We're saying that even though we're probably running this test because we suspect the mean of population 1 is different than the mean of population 2, we're seeing that the variance is the same across both of those populations, right? What we start to get in trouble with is when we have variability in population A that's a lot bigger, a lot smaller than the variability in population B, okay? And we'll talk about this homogeneity of variance thing. This is going to be the bane of your existence, all right? This is the decision point for any number of 1,000 different possibilities that you can go in terms of running your statistical analyses. This is going to be important because it's going to help you decide which of these procedures is going to be the best bet in terms of proceeding with stuff. Okay. Informal assumptions, our data don't contain outliers. Again, that's not new. But then, second, it's not a formal assumption, but it should be that we have relatively equal sample sizes across groups. Now, if you're off by a person or two, it's probably not a big deal. And if you're off by 10 people and you've got 100 people in sample 1 and 90 people in sample 2, that's probably not a big deal, right? But our assumption is, and our statistical proceedings are assuming that you've got relatively equal samples in both groups. If you don't, that starts to complicate and erode your inferences. And so again, between homogeneity of variance and sample size, these are things that you're going to have to look at every time you run a test and then say, okay, based on this information, do I go right or do I go left? So, our formula. Pretty straightforward. We've got the mean of sample 1 minus the mean of sample 2 minus population mean 1 minus population mean 2. Morgan, what happens to this term functionally when we're going through and running our tests?
I can't really say I understand what you mean.
Okay. Do we know our population means? We don't. Well, what do we assume these population means? What's the relation to these population means that we're assuming under the null hypothesis?
Is it just turning to 0?
Yeah, it just turns into 0. Okay, that's gone.
It seemed too simple.
Yep. So this is the technical formula, but because under the null hypothesis form we're assuming equality, this should be the same as that. That turns into 0, and so it just goes away. Okay. But what we've got here, you'll notice, so we end up with mean of population or mean of sample 1 subtracted from the mean of sample 2 over our standard error of the difference in means. Okay. Standard error in the difference in means is going to be our expected difference in means across samples, assuming the null hypothesis is true. Okay. So assuming that population 1 is equal, has an equal population mean population 2. If I just randomly select any two samples from these two populations, Rajiv, would I expect those the mean of those two samples to be identical every time? No, there's always going to be some difference, right? And what our distribution, our standard error of our difference in sample means is going to tell us with replication over an infinite number of trials, if we were to randomly draw samples of a given size from population 1 and population 2 and calculate the difference between those two, how much would we expect those to jump around just based on sampling stuff, okay? And so again, this is giving us our expected difference in mean across samples, assuming the null is true, and is giving us an indicator, just like when we were just calculating our standard error of the mean, tells us what much M1 minus 2 estimates population 1 minus population 2, right? Anytime we're talking about a standard error, the standard error of what you want to make sure that you know, but the interpretation is always going to be identical. It's how well this statistic represents the population parameter. Okay. So, but what gets tricky when we're calculating the standard error of the mean, or excuse me, the standard error of the difference in means, we've got a couple different sources of error. Our sample mean 1 approximates population mean 2, or population mean 1 with some error. It's not even perfect. Then population or sample mean 2 is going to approximate population mean to with some error. And so there's gonna be some stuff there, right? So we've got two different things that are contributing to our error. So as a consequence, our standard error for our difference in sample means, for our independent sample t-test, we need to take into account both of these sources of error. And so to calculate our standard error of our difference in sample means, right? So our standard error for our independent sample t-test is going to be variance of sample 1 over the number of people in sample 1 plus variance in sample 2 over the number of people in sample 2. Okay. So you can see mathematically we've got our first source of error and our second source of error, and these two things together are going to give us our distribution, our standard error of the difference in means. So Angela, if you're looking at this equation relative to the standard error formula that we've been using up to this point, is our standard error for the standard error for the difference in sample means going to be larger or smaller than the standard error of the mean? Absolutely right. Why is that? Exactly. Functionally, we're basically doubling it, right? Because we've got two different sources of error. Okay. And so if we take a look at this graphically, okay, if this is, say, sample 1, and this is sample 2. Sample 1 ranges from 25 to 95, has a range of 70 points. Okay. Population 2, our red value here, ranges from 15 to 65 for a range of 50 points. Okay. And so the question is what is the possible range of two randomly selected scores taken from population 1 and population 2? So we take a look at this for our extreme. If we start with population 1, take the highest value from population 1 is 95, and subtract the lowest value from population 2, right? So we take, and again, if I randomly select, if I just happen to randomly select the highest individual in population 1, and I happen to randomly select the absolute lowest individual from population 2, that gives me a span of 80 points. But on the other extreme, I could grab the lowest person from population 1 for a score of 25, and the highest person in population 2 at 65, which gives me a range of -40. And if I go through and I put this on a number line, right, at the highest, I've got a difference of 80 towards the direction of population 1, or 40 in the direction of population 2. If I take this up, this is a 120 point span. If I add these two ranges, also gives me the same point, right? So basically what this is saying is any two randomly selected scores from this distribution, at most, I could say that population 1 is 80 points above population 2, or I could say alternatively that population 2 is 40 points above population 1, right? And so adding these together, we see the complete range of variance or differences that can be drawn in. And so because of this, right, we've got two populations, we've got not just one, but two ways that we could be completely opposite. On one scenario extreme, we're saying that population 1 is way higher than population 2. On the other extreme, we're saying population 2 is way higher than population of 1. Big range of differences, and so what we have to do is calculate our standard error. The difference in means is a function of the variability in both of our samples. Okay. So again, just a demonstration so that you just don't have to say, take my word for it, that the standard error, the difference in sample means is a function of both population variability. Like this is actually mathematically what we're trying to account for with our independent sample t-test. Okay. Questions on this? All right. Well, we got a problem. right? Up to this point, we say, oh, we've got a sample, and we're assuming informally that our samples are drawn from, are relatively equal. But what if they're not? What if they are? What if I got 10 people in one sample and 30 people in the other, right? That's kind of a big difference, okay? Can we not run an independent sample t-test? Has anybody seen an independent sample t-test where the samples are of different sizes? Yeah, almost always, right? But the problem is that we know that our larger samples, they're doing a better job of estimating variability in the population than our smaller sample sizes. Right? So Katie, in this scenario, which one of these samples should I be expecting to provide a better estimate of population variance than, or a more stable, accurate estimate of population variance than the other?
The sample that is 30.
Yeah, right. So if I'm going through and I'm trying to calculate the standard error, the mean, I should probably want the more accurate estimate to have more weight in terms of calculating my estimate, right? Because I'm assuming, the assumption is that the population variance is equal, right? I know my variances will differ a little bit, but what I want to do is I want to weight the more accurate estimate than the less accurate estimate, right? Because we never have identical estimates of population variance, or only very, very rare occasions. If we have equal sample sizes, or if we have cases with unequal sample sizes, and we just use our regular equation for plugging in standard error of the mean, what's going to happen is the sample with the smaller n is going to have an undue influence on my effect, because I've got a sample with a less precise estimate weighing in more than the sample with the more precise estimate, right? Any individual in the smaller sample is creating, having a larger impact than any individual in the larger sample, right? Think about this as the U.S. Senate, right? we are wildly overpowered in Wyoming, right? All states get two seats, right? One could make the argument that any individual in Wyoming has far more power in the Senate than anybody from, say, California. Same kind of thing going on here, all right? And so what we need to do is we need to adjust for this. And so what we do is we're going to go through and we're going to create a pooled variance, okay? Pooled variance is just going to be a weighted average of our two sample variances here. Pooled variance, I will not ask you to memorize this formula, but you probably will, because you're going to be doing a lot of calculating pooled variances all day, all night, all the time, right? But just wanting you to understand what's going in. Basically, we've got our sample size for sample 1 minus 1. So basically, we've got our degrees of freedom for sample 1 multiplied by the variance of sample 1 plus n minus 1 degrees of freedom from sample 2 and the variance of sample 2 over n plus 1 plus n plus 2 minus 2. This is your degrees of freedom for your overall independent sample t-test, okay? Do not plug in standard deviations in here. That's going to screw you up, okay? Make sure that you're using variance estimates and not standard deviations. So what we do then, if we calculate our pooled estimate, so what we see is the sample with the lower number of people, the smaller sample size, it gets less say in terms of determining pooled variance than the sample with the higher number of people, right? So if we start to have a big imbalance in terms of our sample size, if I've got a sample of 20 and a sample of 60, the sample of 60 is going to go. And so what we then do for our final formula for our independent sample t-test is we're going to take mean 1 minus mean 2, that cancels out, over the standard error, the difference in means. But our standard error for the difference in means, we're going to calculate this as the square root of the pooled variance over sample 1 plus the pooled variance over sample 2. Okay. So this is different. It's still the same structure of formula as what we had originally put together. The only difference here is we're substituting the sample variance for the pooled variance in both of these. Okay? And then our degrees of freedom for our test is going to be sample size 1 plus sample size 2 minus 2 is going to give us our degrees of freedom. Okay? So things that people do. Don't plug in standard deviation estimates. We're working with variance estimates. And don't divide, when you're calculating your standard error, divide your pooled variance by your sample size, not your degrees of freedom, because that will throw you off again too. It'll happen, but try not to let it. Because Candace will catch you. Like, this is not right. Like, this is off to the third decimal place. I'm going to go hunt for the errors. Okay? Questions about this stuff? Okay. Why is it helpful to know, so we talk about degrees of freedom. Any ideas on why it might, what circumstance it might be helpful to know, and why it might be useful to know degrees of freedom? I don't even know if this is showing anymore. This is very helpful when you're reading other people's papers, right? Because if they present in the samples, right, that we have sample 1 had 50 people and sample 2 had 40 people. How many degrees of freedom should be in their t-test? Was it, Maureen? 88. Sometimes you'll curiously find that that's not the degrees of freedom. The degrees of freedom is something else, which suggests what? And maybe if they run like 3 different t-tests, the degrees of freedom for each one of those t-tests is jumping around. What is that? What would you suspect might happen or might be causing that?
They separated groups to find a more specific effect.
What's that now?
They like separated groups to find a more specific effect. Making sense in my head, but it's not out loud.
No, I can see what you're saying. I'm willing to give people a little more credit because then that's just straight up fooling around with data, right? What's probably going on? Yeah, these two groups don't have complete data on different outcome variables. There's certain people have scores missing, and so maybe for this outcome, 48 people in this sample and 39 in the other one have data, and in the other one it's different, right? Which can be a small thing, or it can be a large thing. But what ends up happening is it means you're not comparing the same group of people across. It's a different group of people across each one. I don't like that. Particularly if it's a small amount, you just say, do we just cut it down to a group of people who you have the full sample with and complete data so you can compare across. And if it's big, then you need to tell me that you've got a lot of missing data in here, right? But we sometimes don't like to say that. But knowing what your degrees of freedom, and it can also help you make a determination on what they're actually doing, because sometimes people aren't good at communicating what they're doing, all right? So degrees of freedom, kind of a sort of a side thing going on, but go through, take a look, and that can be helpful in determining, doing some investigatory work on what's happening and stuff. Okay. Talk about effect sizes, and then we'll go through, let you guys take a break. When we get into our independent sample t-test, there's a number of different effect sizes we can use, and it's going to be up to you to think about, what am I trying to do? What are the characteristics of my data? Based on those 2 questions, which one of these effect sizes is going to be the best to use? Okay? So just like with our single sample test, raw difference of the means, this can be a reasonable metric, right? And when is this going to be the most a more effective metric? Just looking at the difference, raw difference, to determine an effect, the magnitude of an effect. What do you think, Rajiv? When might this be something that would be important to report or emphasize?
So, pretty important when we just want to see the mean of the 2 different populations and just infer like if they are different or not, or if they're really close enough.
Right. And so when is that going to be most meaningful? Do we have an idea? That can be, if we've got small variance, certainly, because that's gonna give us a better sense. What about if we're talking about things like scores on a random personality test that are arbitrary versus if we're talking about dollars or years of life or height in inches or things along those lines? This can be incredibly powerful if we're talking about actual units that people care about. Generally, we're not. We're talking about random scales with random cut points and things along those lines, right? If I tell you that the mean of my sample has a PCL5 score of 56, what does that mean to anybody? Nothing, right? But if I start telling you about talking about things in terms of real life, if I say individuals in my PTSD sample are making $30,000 a year less than people without PTSD, that tells you something, right? And so if you were working in a field, or if we're working with some outcome that has some meaningful intuitive metric, this can be a nice way to just say, look, like this is the difference we're seeing in these groups, and this is a big deal, right? Now, oftentimes we're not dealing with that, right? So we're falling back into some sort of standardized measure of effect. Cohen's D, okay? Cohen's original conceptualization of this, if you look back in Cohen's text, I've got a copy. I'll let you read it if you don't steal it, right? If you're wearing gloves or something like that. What Cohen is recommending is we take the mean of sample 1, mean of sample 2 over the standard deviation. Okay? What's maybe the concern with that? Why might this be confusing in an independent sample t-test? What do you think, Alex?
Which standard deviation?
Exactly, which standard deviation, all right? I've got two of them. Which one do I don't know what S means. Which one do I use, right? And what would Cohen maybe say, based on the assumptions of the t-test? Cohen might say it doesn't matter, the homogeneity variance. The assumption is that they're the same, so I don't know, either one, doesn't matter, right? What's the practical problem with that? Am I typically looking for wanting to report larger or smaller effects? Larger effects. And so if I have two standard deviations and I need to calculate an effect size, Stephanie, which one am I going to be tempted to choose as my best standard deviation to use? The smaller one, right? And so we've got conceptually, right? The conceptualization of Cohen's D for an independent sample t-test is mean 1 minus mean 2 over the standard deviation. But from an applied standpoint, this gets tricky, okay? So we've got a couple different things we can go through and think about using in terms of what standard deviation to choose, okay? One, we can use something that is often referred to as Glass's delta. Glass's delta is mean 1 minus mean 2 over the standard deviation of the control group. This is a nice metric to use if you've got some control group that has some that is meaningful in some way. Okay? I'm running an experimental study, and I've got this group that got some sort of standard control condition, and then I've got this other group that got some experimental condition. Glass's delta is nice because what we can do is start to interpret this in terms of differences in the mean relative to the variability that we would expect if we just weren't doing anything at all, right? If given just a standard baseline state of affairs, just based on sort of how we would expect things to operate in the universe, this is the amount of difference we get in terms of standard deviation, okay? Or for you clinical people, if I'm running a treatment, right, and I've got a bunch of people who are depressed, and we gave them a placebo or something like that, and we're just sort of looking at where their scores are after 8 weeks, and then we've got a group of people who got an active treatment, and we're looking at where their scores are at 8 weeks, right? What might be helpful and might be intuitive is I might then use standard deviation of my control group and frame and standardize my effect size in terms of variability for the people who just didn't have anything doing at all, right? And so we would see, based on variability that we see in the control group, we find that our treatment group is scoring 0.8 of a standard deviation below our controls on some outcome, right? So glasses delta is a nice metric to use if you've got some meaningful control or reference group that nothing happened to them, right? Because then we're just saying that this is how much difference we see in units of standard deviation based on variability that we would just normally expect out there in the universe anyway. Okay? People understand just kind of what the benefit of glasses delta is. But sometimes we don't have a good control group, right? Sometimes we're comparing condition A and condition B, and both condition A and condition B we did something to them, right? They're not normal, they're not a typical group of people because we stress this group out this way and we stress this group out this way. So there's no real good control group, right, to base this on, nothing that's meaningful, right? And in this case, what we will see is the calculation of what's often referred to as Hedges G. Hedges gets credited for this. Oftentimes they'll just report this as D, but this is why you always want to make sure that you're communicating to people what you're standardizing your effect with. What we're doing here, mean 1 minus mean 2 over our pooled variance, or our pooled standard deviation. Okay? This is nice. This alleviates you of the need to decide which standard deviation to use, because I'm just going to use a pooled standard deviation. This is probably the most common that we see, right? And oftentimes this is going to be the most defensible, but would encourage you not to overlook glasses delta if you've got a true control group that's meaningful in terms of making some interpretations there. Last thing we've got is Hedges unbiased G. What we find is that for small samples, our effect sizes tend to be inflated, okay? Because for small samples, on any random selection of a small sample variance, is that variance likely to be lower than the population variance or higher than the population variance? Lower, right? Remember we talked about that skewed distribution. So for the mean of this distribution of sample variances is equal to the population variance. If I random, because it's a skewed distribution, if I just randomly pluck one out, chances are I'm going to get one that's too small. And so this is particularly problematic with small samples. And so what we see is that if we're working and calculating effect sizes with samples that are particularly small, our Hedges G will be too large. And so what Hedges unbiased G does is it institutes a correction for the size of your sample. And on this graph here, we see as the sample, or as our degrees of freedom, which corresponds to our sample size, right, gets larger and larger, the impact on our effect size G versus Hedges G starts to decrease, right? So by the time you get to degrees of freedom 50, right, the difference between G and unbiased G is going to start to become increasingly small. But basically what we're doing with Hedges unbiased G, calculate G, calculate Hedges G, and then just multiply this by 1 minus 3 over 4 times sample 1 plus sample 2 minus 2 minus 1. It's just a correction. This is going to be a number that's less than 1, right? And anytime we multiply something by a number less than 1, what does it do to our outcome? Drives it down, right? But as our sample sizes get larger and larger, this value is going to get closer and closer to 1, right? And so what ends up happening is we get a big correction for for our effect size in small samples and a smaller correction for larger samples. And so when you should be using this, it's sort of up to you, right? I mean, if you've got a test that has, 20 degrees of freedom, might be worth calculating that, right? Knowing that Hedges G is going to overestimate our effect size. Why are we worried about overestimating our effect size? Because we do it all the time in literature anyway, right? Because we only publish studies that meet statistical significance. And those, if we think about, here's our probable distribution of effect sizes. These are the ones that are most likely to achieve statistical significance given our low power. And so we're probably already massively overestimating effect sizes for anything we publish anyway. And so this is going to be another thing as we're going through thinking about which effect size to use, thinking about what's my sample, do I have equal variances, do I have equal samples, and then am I gonna choose something that's gonna systematically overestimate my effect size? This is a difficult thing to do because, again, we always wanna have the biggest effect size as possible, but being responsible, I can't be responsible for your choices once you get out of this class, but this should at least be something that you're thinking about in terms of good practice reporting. Okay? So these are some options to think about in terms of your effect size. However, from your secondary analyses, there's some different ways that you can drive an effect size, because sometimes people won't give you means and standard deviations, although they always should. But we can get an estimate of D. If someone gives you T values and you know the sample sizes, you just plug all that information in and get an approximation of your effect size here. Or simplify this. This is an alternative form. You can just take 2 times the test statistic over the square root of the degrees of freedom. Is going to give you an approximation of Cohen's D. Okay. For the stuff we're doing, do this, okay? But if you need to pull information from other articles, this is something you can also do. So again, interpretation of these effect sizes is, say I get small, medium, and large. We say that you get a medium effect size of 0.5. We're saying that average score in this group was about a half a standard deviation above the score in the other group, right? Interpreting just the same as we would an effect, or excuse me, a z-score. Only thing that I'm going to encourage you guys to make sure that you're doing is specifying, one, what your standardizer is, right? Are you using just some random? We elected in this study to choose the smaller of the 2 standard deviations because it made our effect sizes look better. Right? Don't say that; that won't get away with that. But if you identify glasses delta, right? Talking about using standard deviation of a control group and Y, pooled standard deviation, or if you elect to create some put together an unbiased G, show why you're doing that. Okay. Questions on this? All right, cool. We'll come back with an example. You guys go take a break, and we'll catch up when you get back. I'm gonna run through a example here. Are we talking about books in the library again? No. Sesame Street. Sesame. They gotta get mad at my own examples because they suck. I'm like, I wish this guy would get better examples. All right. So, example of hypothetical independent sample t-test. So, researchers interested in school performance, students having viewed Sesame Street as a child and those who did not. Scholastic performance in 10 high school students having viewed Sesame Street as kids were compared with 10 students who had not. Students having watched the program had a mean grade of 93, the variance of 22.2, while those not watching, having watched, had a mean grade of 85, variance of 17.8. Okay. As you're working through these problems, important to go through and read what they're doing so that you can appropriately identify populations. Okay. So first thing, in a sentence, state the null hypotheses to be tested. Can someone give me what's the null hypotheses we're testing within this example? Kitty, can you tell me? I was gonna pick Lauren, but she had no. No, don't eat your banana. I was making a joke about like asking you to sort of.
I would, yeah.
Like right
So
after you've
now
taken
all
a
of
bite
us
of
are
food,
huge
right?
amounts of
When we're all at a time, like constantly.
Everybody's like, oh.
Constantly eating.
Everybody's like chipmunk cheeks. Can you give me the null hypothesis in a statement?
That children who use Sesame Street and children who don't use Sesame Street will have the same school performance.
Okay. You're sort of in the right area. All right. What might be, if we were to just make a commentary, not criticisms, on this? Like, so what other elements might we want to clarify or use in terms of stating our null hypothesis here? Okay, we could include that, but if we're okay, right, and we're talking about the difference, right? What but are we, if we go through and read the example, like who are we talking, what's our population here? High school students, okay? And this starts to become important when you're making interpretations, having a good sense for what's going on. So if you just read through this quickly, you might say, oh, we've got elementary school kids who watch Sesame Street and don't, but that's actually not what we're looking at, right? We're looking at high school students who have watched Sesame Street as children and then looking at their performance later on in high school, right? And so wanting to be very specific about what population we're talking about here, right? And so, infinite number of ways you can go through and phrase this, but maybe something along the lines of, say our null hypothesis is that scholastic performance in the population of high school students previously exposed to Sesame Street is equal to the average scholastic performance of high school students not exposed to Sesame Street as children, or something like that, right? Oftentimes, the task with this is to figure out, okay, how do I get my relevant information into this statement and exclude stuff that's not relevant. And so for our symbols, we got the mean of Sesame Street equals mean of no Sesame Street, right? Alternate, mean of Sesame Street not equal to mean of no Sesame Street. That's pretty easy and straightforward, right? Before we move on, people get kind of what I'm looking for in terms of statement of the null hypotheses. Okay, and again, this isn't just for me to make you say words. It's trying to facilitate thinking about sort of getting a close look, seeing what is actually being done, and then thinking about what the population is that we're talking about, where we're drawing our sample from, things like that. Yeah.
Is this not how we wanted to do the like, maybe something else, where it's like the mean of one minus the mean of the other equals 0? Or something
Oh,
equals 0?
no, yeah, you're right. Thank you. Almost ones. Okay, perfect, yeah. You like what I did there? I was like, oh, hey, do it this way, and then I did the way I told you not to do it. So I can be mad at you later on, right? And like, oh, those students don't ever listen. Right? Good catch, thank you very much. I withdraw my threat to punch you.
Re-earned.
So is the second one does not equal 0? Yeah.
Oh, yep. Disaster.
You're just testing us, making sure we're paying
No, no, that actually is fantastic. Like, I don't know if there's a better sort of, because it means you're paying attention, and you're like, that doesn't make sense versus just, you should never just listen to me, because I'm probably not giving you good information. Always question.
So in our words, like when we were stating the null hypothesis, you, like, the way you said it was more like how you wrote it out, right? So like, does that
I
make
don't.
sense when you say like the difference
Yeah, I don't. Yeah.
between, there is no difference?
In your statement, I don't care about how you state that, because the idea is that the statement is you demonstrating that you can communicate in the English language kind of what's going on conceptually at a level, right? And then this ends up being a quicker, shorthand, easier way to do it. Okay. All right. So first thing we're going to do is calculate 95% confidence interval for the difference in grades across samples. Okay. Someone tell me what I need to do first in order to calculate my 95% confidence interval. Okay. Yes. The standard error of what?
Good question, that's all I thought.
So, our standard error, conditioning, you like wake up in the middle of the night screaming standard error. Lorna's standard error of what here? Got the standard error of the difference in means, right?
Okay, yeah.
Okay. And what did we talk about in terms of standard error difference in means? Right, we had talked about, now in this case we actually don't need to do it, but we'll do it anyway. Oftentimes you're going to be using the pooled variance estimate. Just assume that you're going to use a pooled. Now technically, Rajiv, do we need to use a pooled variance estimate in this situation?
No,
Why not?
because we have the same population.
Yeah, right. It says we have the same sample size, right? So we can literally take variance 1 plus variance 2 divided by 2, and that gives us the average variance, right? But what we'll do is we'll walk through an example of using pooled variance just so you can see a demonstration of how we would do that, right? So our pooled variance is going to be n1 minus 1 times our variance for our first group plus n1 minus, or n2 minus 1 times our second variance all over n1 plus n2 minus 2. So in this case, we're going to have 9, right? That's 10 minus 1 times 22.2 plus 9, 17.8, all over, what's our degrees of freedom? What's that?
80.
Oh,
Oh, I'm sorry.
18.
18.
I wrote 10, right? We're trying to pretend I wrote an 18. It's not. All right. What do I get for my pooled variance estimate?
2.2.
My pooled variance estimate.
Is it just the top row?
No, the whole thing.
20.
20, yeah.
Oh,
Okay.
plus, not minus. There we go.
Okay. So you're going to pull this, and so this is obviously a contrived example. We get a pooled variance estimate of exactly 20, right? But, Rajiv, what happens if I get 22.2 plus 17.8 and divide that by 2? What's the number I get?
22 plus 17. It's 20.
20, right? It's the same thing, right? So again, in this example, we didn't need to use the pooled variance equation because we have equal samples, right? Both variance estimates get equal weight in terms of determining our pooled sample variance. But as you go through and do this, the vast majority of the time you'll not be using equal samples, and so we will need to use a pooled estimate. And what our pooled estimate is going to do is it's going to weight more heavily the variances associated with this larger sample relative to the smaller sample. Okay. So I've got my pooled variance estimate. Now what do I need to do? Here we go, Laura. Now jump in. Now what do we need to calculate? Standard error, right? And here, remember our standard error for our independent samples groups is going to be our pooled variance over N1 plus our pooled variance over N2. Okay. So here, we've got square root of 20 over, oops, yeah, 20 over 10 plus 20 over 10, which gives us what? 2. Beautiful round numbers. Okay, perfect. All right. So now we've got our standard error.
Can I ask a question real quick?
Yeah.
Is that what the square root?
What's up?
So the square root of 2?
Nope.
The square root of 4?
So we got 20 divided by 10 is 2. 20 divided by 10 is 2. 2 plus 2 is 4.
I was prematurely adding. My bad.
Yeah. No, this is another thing too, right? Like we're sort of jumping back into middle school, high school math with orders of operations and things like that. This will screw you up, so make sure that you're doing things appropriately, okay? All right, so now, got our 95% confidence interval is going to equal, what do we need to put in there first? What's our point estimate, Rajiv?
93 for the first group.
Right, 93
Minus
minus 85, which is going to give us what?
8.
8, perfect. 8, this is our point estimate for the difference. If you say, what is the actual difference between these population estimates, you're gonna say, well, I don't know, but my best guess is 8, right? So we've got 8 plus or minus, what's the next value we need here?
1.96.
What's that?
1.96.
You're on the right track, but not quite 1.96. Why is it not 1.96? Because it's a T, right? So what's the critical value we need to calculate for this? What's that? What's that? How many degrees of freedom do we use? 18, right? Yep.
2.101.
What do we get?
2.101.
2.101. Okay, this is another place that could get people tripped up. We don't have population estimates, right? So we can't use critical values from a z-test, right? We have to use the critical value based on the degrees of freedom that we have available to us, right, in our test. We're using an independent sample t-test. Degrees of freedom are sample 1 plus sample 2 minus 2. In this case, it's 18, and so we would go through on our t-table, find 18 degrees of freedom, level of confidence, that's going to be our critical value. As we start to get into things that aren't nice round numbers, use those critical value websites that we posted in the last, or that we talked about in the last lecture, to go through and figure out what your exact critical value should be for a given degrees of freedom. You're not going to find, 43 degrees of freedom probably on a table, but you can get it using the magic of the internet. Okay, so please go through and do that. So, and then what's the last thing we need to throw in here? What's that? Standard error, right? 2, okay? Which gives us confidence interval of a lower bound of the difference in scholastic achievement of 3.8 and an upper bound of 12.20. And Morgan, can you give me a practical interpretation of this confidence interval?
You could expect that the difference between like two randomly selected populations would be within these ranges, within this range.
Okay, yeah. What I would like you to do is fill some of that stuff out, because then that stuff starts to make this more real, right? Because our outcome variable is grade, right? And so what we can do is we start thinking about, so we would expect the difference in average grade of population of high school students having watched Sesame Street versus those who haven't, to be a difference between 3.8 and 12.2, right? And thinking about, if we're talking about grades, and assuming this is a 0 to 100 scale in grades, Katie, is this a very precise estimate?
Very precise estimate.
Yeah, is it very precise?
Yes.
What's that?
Yes.
Yeah, I mean, it's within 9 points-ish, right? So, but in terms of, we're thinking about grades, right? I mean, this is anywhere from a 3-point difference to a 12-point difference if we're thinking on a 90 to 100, 80 to 90, 70 to 80, like that type of scale, right? We're on average thinking about close to a letter grade difference, right? But our range could be anywhere from, pretty high to pretty low, right? And so, I mean, it's okay. It's not a 2 grade point on a higher end to nothing on the top end, right? But again, wanting you to start thinking about, okay, what's my outcome, and like, what does this mean in practical terms? And what's nice, if we're thinking about this clearly, it takes a little extra effort, but we have to think about, like, okay, well, I mean, we're talking about anywhere from a full letter grade, which is kind of a big deal, to under half of the letter. I mean, 3, 4, it's not small. I mean, it's reasonable size, right? But again, what would help us get more precision on this estimate? So, What would make that confidence interval smaller? Yeah, I mean, we got 10 people in each sample. This is really small, right? I have very little confidence that this is a reasonable estimate of our actual population parameters. But what do we already suspect, or should not suspect, know for a fact, already based on the calculation of the difference in population means and the confidence interval around that? Is this a reliable effect? What do you think, Katie? Yeah, how do you know?
Because it's close to a laboratory difference between the groups.
Okay, on the upper end, but what's the thing about this interval that really tells us that we've are going to find a reliable impact of Sesame Street on achievement here?
The calculated difference falls in the range.
What's that?
The calculated difference of 8 falls in this range.
Well, no, 8 has to fall in the range because
Oh,
that's
yeah.
what we're calculating the confidence interval around.
Does it contain 0?
Exactly. It doesn't contain 0, right? So basically, an estimate of no difference, an estimate of 0 difference, is not a plausible value based on our calculation of the confidence interval, right? No difference is not a reasonable value. It falls outside the lower bound of what we would deem to be an acceptable estimate based on the data that we've collected, right? So we already know that when we eventually get to our t-test, we're already going to reject the null hypothesis, right? We know that for a fact. But what starts to happen is we can start to say, well, not only is it not a difference, right? We're expecting this difference to range anywhere in the population from 3.8 to 12.2 points, right? Which is a much more satisfying and meaningful interpretation than, yeah, it just makes a difference, right? Okay. So we've got that. And then we want to provide an index of the magnitude of effect size for these data. What type of effect size might we want to calculate for this problem? What would make the most sense?
Can I ask a question?
Yeah.
What added information does the alpha, like does the p-value give us that the 95% confidence interval does not?
Many would argue not anything meaningful, right? Which is the full push behind why we should be moving towards effect sizes, period, and just not even worry about p-values. But we need to report p-values because I'm not going to send you out in the universe as moral soldiers and not report p-values because you'll get yourself into trouble because people won't want you to do that, right? So, but what I do want you to do is on these assignments having you calculate confidence intervals and making strong interpretations of that. So by the time we get to p-values, it's just mostly just sort of writing up statistics, right, and giving people what they want. But it's even though convention will force you to provide p-values in almost every single journal, that doesn't mean that you can't incorporate good, meaningful interpretations of your effect sizes and confidence intervals and just provide a much better accounting of your science. So, okay. In terms of our effect sizes, what are our options in terms of calculating an effect size for this?
You can use glass.
Yeah, we could use a glasses delta, and why could we use a glasses delta here? Yeah, right. So these are just people who haven't been exposed to Sesame Street, right? So in the absence of our construct might be educational programming, right? Like it's a specific type of educational programming, but in the absence of that, right, that could be a meaningful estimate, right? So we could calculate delta is equal to 8, right? The difference between our two means over what's our standardizer? What's the value of our standardizer going to be?
Oh, I'm okay for
Yeah.
So square root of
Okay, and what's the square root of 17.8?
4.219.
4.218. 19, okay, which gives us a glasses delta of what? 1.896. We'll call it 1.90, okay? What's our other option? What else could we use? Ends up being kind of the standard default for effect sizes in a lot of cases. Edge is G, right? Right? And here, we're gonna take 8 over our standard deviation, gonna be our pooled variance, 20, what's the square root of 20? 4.47, what? 2, which gives us an effect size of 1.79, right? So we get a slight variation in our effect size based on which one of these metrics we use. I agree. I think for this case, I think glasses delta actually makes for a meaningful interpretation. And so we're going to standardize our effect based on variability in the based on our estimate of variability in the population of individuals who haven't been exposed to educational programming. Given these data, we're seeing that individuals, high schoolers who have been previously exposed to Sesame Street's children are scoring about close to 2 standard deviations above the mean of their high schoolers who haven't been exposed to educational programming, right? Or you could just say, you know, based on a pooled variance estimate, we're seeing about 1.8 standard deviations, scoring about 1.8 standard deviations higher in terms of grades than high schoolers not exposed to educational programming, right? And again, this is a big deal, right? This is a huge, massive effect. If this was a real effect for Sesame Street, we should put all our educational money into Sesame Street and just have people be required to watch Sesame Street, because this is a massive, massive effect, right? So, okay, questions about effect size or how we started thinking about which one of our options might be most defensible in terms of calculating things.
So for example, if I use the Hayes like calculate the Z, like the G, will that be wrong?
What's that now?
If I don't calculate the glass delta and do the Hayes effect size, will that be wrong?
I would probably question, like, maybe. If you gave me a strong rationale, because in these assignments I'm going to ask you to give me a rationale for why the effect size that you chose. And this can happen, right? Like, we might disagree on which one's the best, but if you give me a good, strong explanation where I can say, fair enough, right? Then that's fine, right?
So
but
in this case, like since the population is just 10, like the sample is just 10 people, so I was thinking like to use this Hayes than the glass delta. Is that a really defensive like argument to use this effect size?
well, probably, given the small sample in this thing, we should probably use Hedges unbiased, right? I mean, this is exactly the situation, and also the fact that we have a massive effect size would maybe suggest that we might have overshot our mark a little bit right here. So generally, right, in this situation, you could say glasses delta because we have a control group, or you could say unbiased G because we've got a really small effect size. Couching this within the standard in terms of variance of the control doesn't outweigh the fact that we're using incredibly small samples. And so either one of those I would probably accept as reasonable arguments for one of those. Any other questions about effect sizes here? Okay. And then finally what we're going to do, conduct a hypothesis test at alpha equal 0.05. By the time we've got here, we've got all the numbers and pieces and parts we need, right? We've got our t-test is going to be 93 minus 85 over what? Standard error, right? Which is what? 2,
Two, yeah.
right? Which gives us a T of 4, right? And what was our critical value? What was it, Sam? Okay. T critical 2.101. Sorry about that, Raji. All this is behind the screen. You can't see it. T critical 2.101. Have we exceeded our threshold for claiming statistical significance, Sam? Yeah, by quite a bit, right? And if we go through and take a look at our p-value for a t statistic of 4 with 18 degrees of freedom, we find that our corresponding p-value is p less than 0.001 if I'm using the graph pad to go through and plug that out, right? And so we would conclude that we have sufficient evidence to reject the null hypothesis in this case. And so what do these data as a whole suggest in terms of the impact of exposure to Sesame Street as in childhood?
Do you want the long statistical answer, or do you just want like the practical?
Practical summary, yeah.
People seem to score, like high schoolers seem to be better in like grade wise. They seem to score
Right.
better than people who are exposed to.
Right, and higher by quite a bit, you know, closest 2 standard deviations higher in terms of their grades. Now, did Sesame Street cause higher grades in these individuals? Yeah, I don't know, right? I mean, there's a lot of factors that could be driving increased performance, and Sesame Street is just a proxy for a lot of different things, right? But, at least in terms of this, suggesting that there at least is a relation between, based on these data, we have sufficient evidence to say that there is a relation between exposure to Sesame Street in childhood and later grades. You're smiling. What do you think?
It's kind of embarrassing, but when you said Sesame Street could be a proxy for something else, well, when I was younger, I didn't speak English, so I watched Plaza Sésamo.
Okay.
So it's just the Spanish version of Sesame Street, and that was like a proxy in my mind. So
Yeah.
it just
Nice.
made me laugh at my Spanish mom and both.
That's all right. That's right. About the only Spanish I have command of is things that I watched on Sesame Street, I think, when I was a child. So. Okay, but so this is an example of a hand problem that we would go through and work through. People comfortable with what we've got going on here? Okay, cool. So, have another problem here, right? What happens though if our estimates of our population variance are not equal? Assumption is that our population variances are equal, right? But what if they're not? What if, based on our sample, we have evidence that probably the variance of population 1 is substantial? Is that all of a sudden the sampling distribution of our t-test doesn't follow standard sampling distribution of a t-test, right? If our t-tests, mathematically assuming equal population variance, that's the distribution of our t-test, and that's what's in our tables. With unequal variances, our sampling distribution, our t-tests aren't doing this anymore, right? And if they're not doing this anymore, Raji, what does this do to our hypothesis tests?
I'm sorry, I was lost.
Okay, so we're saying if this is a sampling distribution of t with 18 degrees of freedom, assuming equal sample variances, right? What happens if now the sampling distribution that I get, if my populations, if I don't have equal population variance, what does that do to my inferences?
change the. I'm not sure.
Throws them all out of whack, right? The entire sort of process of inferential statistics is this idea that we have some known distribution of scores, and based on that known distribution of scores, that hypothetical distribution of scores, we can start assigning probability values to certain values, right? But if I'm calculating a statistic that should follow this distribution, but now it doesn't because I've violated assumptions, I don't know if I start to very quickly lose confidence in my conclusions based on this, right? Because I don't know what the sampling distribution of this statistic is with unequal variances, but it's not what I'm testing against. And so now all of a sudden, so my criterion's all off, and I might say that I have sufficient evidence to reject the null hypothesis, but I actually don't know that because the statistic I calculated, it's a wild card. It's gone rogue. It's part of a completely different distribution that I don't know anything about, right? I can say, oh, it should follow this distribution, but I know that it doesn't, and then that starts to become problematic, okay? And this is what happens when we violate the assumptions of our tests. Our test statistics that are assumed to follow these nice distributions that we have in books and calculators and things like that no longer do. They've got a different distribution, and if they've got a different distribution that we don't know about, then it's problematic because we can't assign probability values because the probability values are all based on area under the curve and where these values are falling and things like that, okay? So this is problematic. And so what we have is a new distribution, right? We've got a new sampling distribution of T prime, and T prime, we don't know what the sampling distribution of T prime is. It's something, we just don't know what it is. And so if we start pretending like T prime follows a sampling distribution of our known T's and making decisions based on that, things start to get out of whack, okay? And again, this is the problem. Anytime you see violation of assumptions, this is why we start to lose confidence in our inferences, because the test statistic we're calculating doesn't follow the same distribution as the test statistic we want it to, and now all of a sudden, things start to get messed up, okay? So, people long ago recognized that this is an issue, right? And so a couple of solutions, and Hal does a nice job of walking through this, talking about a Behrens-Fisher approach. Behrens-Fisher basically tabled the distribution of T prime, but for a specific number of distributions, right? There's lots of different ways that population 1 variance could be different than population 2 variance, and then we start adding in different sample sizes and things like that. Tabling out all possible combinations start to get unreasonable, right? And so this is a little bit, this is limited. What we do now, and what SPSS will do, is put together a Welch-Satterthwaite solution. With a Welch-Satterthwaite solution, what is going on is we've got we have evidence of unequal population variances, right? And so now we're not calculating T, we're calculating some T prime. With Welch-Satterthwaite, T prime interpreted as a legitimate member of the T family, but we just don't know what degrees of freedom it is, right? So T prime is a wild card. We know it follows a T distribution. We're assuming it's following a T distribution. We just don't know which one, right? It should be 18, but we violated our assumptions of homogeneity of variance, and so I don't know which one of these T curves to test this on, right? And so what we do then is estimate our degrees of freedom as a function of our sample variances and our sample sizes of each group. And so with this solution, what SPSS is going to do, and I at one point had people calculate this out by hand and then decided that wasn't a good use of your time. It's pretty involved. But essentially what we're doing is we're saying, okay, we violated our homogeneity variance assumptions. We're still going to assume that T prime follows a T distribution, but what we're going to do is we're going to estimate which distribution it's following based on the variances and the sample sizes of each one of your groups. Okay? When we determine whether or not we need to fall into this Welch-Satterthwaite solution, And in SPSS, this is gonna give us a sample with equal variances not assumed, is we're gonna take a look at our Levine's test. Now, Levine's test is problematic for a lot of reasons, but for right now, we'll just assume that it's okay for our purposes. Basically, a Levine's test is it's gonna give us, every time we run an analysis, we're gonna start out and take a look at our Levine's test and take a look and see whether or not our Levine's test is statistically significant. If Levine's test is statistically significant, what do you think that means? Knowing what we know about hypothesis testing. What are we usually testing with a hypothesis test mathematically? What do you think, Steph? In a null hypothesis, what are we talked about, like we're almost always testing at some level?
That there's no differences in.
Yeah, right, that something is equal to 0, right? And so if we have a significant Levine's test, what would you guess that means?
Levine's are different.
Yeah, then we got a different, and so what are we hoping to see in our Levine's test?
Not significant.
That it's not significant, right? So if we have a significant Levine's test, and there are some limitations with this, but it suggests that we may have unequal variances, or the population variances from which these samples are drawn are not equal, okay? Essentially, what Levine's test is doing is it's taking each score and replacing each score in your sample with its deviation from the sample mean. Okay? So if we have values of x that are 2, 7, 9, 1, 0, 4, right? What we're going to do is we're going to go difference here, and what's the sample mean here? 2, 7, 9, 1, 1. You got a sample mean of 3.83. Okay. Basically what Levine's test is doing is it's taking each one of these scores and subtracting it from 3.83, right? So this one's going to be, this is going to be a negative, that's going to be a positive, positive, negative, negative, positive, right? And so what happens if we just add all these up? What are we going to get? You can give us 0, right? But what Levine's is doing is it's going to replace these deviation scores with either the square or just the absolute value, right? And so we're going to do this, take the deviation score, the absolute deviation score for sample 1, and the mean deviation score, absolute deviation score for sample 2. And then we're just going to run an independent sample t-test using the mean of those 2 deviation scores. And if we find that the average deviation in sample 1 is different than the average deviation in sample 2, what do we conclude? That we've got unequal variances, right? And so, assuming that we have equal variances, our deviation scores, the difference in our deviation score should be different than 0. This is what Levine's test is doing in the background, okay? So, but if we're using this as our test of whether or not we've made a violation of our underlying assumptions, given what we've talked about already about sample size and power and things along those lines, what's a concern that we might have for our Levine's test? Does someone anticipate the criticism of Levine's? If we have a really big sample, what's Levine's test probably going to tell us? Based on your understanding of statistical power. We have a really powerful test. What are we going to do? We're gonna pick out very, very small differences, right? And our assumption isn't necessarily that they're identical, right? But if we've got really, really large samples, what's gonna happen to our Levine's test? It's pretty likely that it's gonna be statistically significant. Even if my variances deviate only a little bit from one another, it's gonna tell me that I've got evidence that they're significantly different than zero, right? That's not saying that they're meaningfully different than zero, it's just saying that there's something there, right? So if I've got 50 people in one sample and 60 people in the other, it's a pretty powerful test, right? So what it's telling me is that I've made a violation when maybe I don't need to be terribly concerned about that, right? I may have a violation, but it may not be a huge issue, right? Alternatively, if I've got very, very small samples, right, what's that going to do to the power of my Levine's test? Will I have a lot of power to detect effects or not? What do you think, Katie? Not, right? And so I might look at my Levine's test and say, well, I haven't violated homogeneity of variance because I didn't get a significant Levine's test in my cell size of 5 and 6, right? I might have a substantial difference between my estimates, right? That just aren't being picked up because I have low power, right? And so this is the same reason we don't rely on statistical tests for skew and kurtosis, because our statistical tests for skew and kurtosis are asking the question whether or not skew and kurtosis are different than what? 0, right? Do our skew and kurtosis for our test need to absolutely be 0? No. And so it's particularly as we get larger and larger samples, we say, oh, we have significant skew at p less than 0.001 in our sample of 400. Well, of course you do, right? Like at that level, like any marginal deviation from perfectly normal is going to cause a problem, or is going to register as statistically significant. But are we worried about marginal deviations from normality? No, right? And so this is one of the things we want you all to be careful of and mindful of as you're going through and evaluating and making interpretations of statistics. Okay, so people kind of get to see the kind of what we're doing here with this set of analyses. Okay, so we tend to here, and there's evidence for that our means-based tests are fairly robust to violations. That means that even when we have violations, we have unequal samples or unequal variances or really ugly distributions, these tend to be fairly robust to, our inferences tend to be fairly robust to these violations. And this is a true statement, okay? I've run t-tests where my actual observed scores are really, really, really ugly. Understanding that the assumption is the distribution of sample means, but it's still really, really ugly, right? And our means-based tests are robust, but what ends up happening is they're robust until we start doubling down on violations, okay? Minimal impact of violations of variance, right? So if we have if our variances are unequal, we're still okay, assuming we have an equal sample size. Minimal impact of non-normality, assuming a reasonable N and distributions that are similarly shaped, right? If I've got a reasonably sized sample and my distributions are skewed, but they're both skewed in the same direction, I'm doing pretty good, right? But if they're skewed in different directions, if sample A has a real huge positive skew, sample B has a real huge negative skew, we need to start to become worried about that, right? So in our screening, that should detect that something's problematic, okay? Situations where we're not robust, different shape and unequal variance, right? If we've got skewed distributions or a normal distribution and a really skewed distribution, and our variances are also unequal, particularly if our distributions are skewed in opposite directions, we've got problems, okay? So we've taken one violation and then added another one to it, and now we've got some difficulties here. If we've got unequal variance and unequal sample size, right? In this case, we can start to kind of predict on the impact of what this will have. If the larger sample has a larger variance, we get too conservative of a test. Why is this, Lauren? For a larger sample has a larger variance, why is this going to make our test too conservative? the substantially larger sample has a substantially larger variance estimate, how's that gonna weight our pooled variance? Is our pooled variance gonna be large or small? It's gonna be large, right? Because we've got the larger sample with a substantially larger variance, so our pooled variance is gonna be large. And if our pooled variance is large, what's that gonna make our standard error have? What's gonna happen to our standard error, Angela? It's gonna be large. And if we were dividing our test, and if we were including a larger standard error in our test statistic, what that's gonna do to our test statistic? It's gonna make it small, right? It's gonna be harder, and so we're gonna have a test that's too conservative because we're gonna have suppression in our test. However, if our larger sample has a smaller variance, then the bigger sample has substantially smaller variance. It's gonna be our pooled variance is gonna be skewed too far toward the smaller end. It's gonna make our standard error too big or too small. Too small, Angela. Too small. And so what that's gonna do to our test statistic? It's gonna inflate it, right? So we've got too liberal a test, right? And so this can be helpful in thinking about what the consequences are mathematically. If you think, okay, I've overestimated my variance, underestimated my variance, what are the consequences gonna be? Understanding sort of all the stuff I've beaten you over the head with for the past several weeks is gonna be helpful with that, okay? Or if we have violations of normality in small sample sizes, right? I've got crazy skewed data and a cell size of 10. That's a problem. I'm probably need to be worried about that and impact things along those lines. Now, if we've got reasonably sized cells, about 25 or more, that's going to give us some confidence that we can sort of be robust at things. But again, always take this with a grain of salt, right? You can't say like, oh, I've got 26 people in my sample, and so I don't need to be worried about the distribution of my scores. Go through, take a look, and recognize that you may start to have problems with that. Okay. Questions on when we're robust and when we're not robust, and the impact that it has, particularly in terms of unequal variance and unequal sample sizes? Okay. Like this stuff can start to be helpful, right? Because if you know you made a violation and you know the likely impact that that'll have on your test, right? If I run a test and I've got unequal variances and unequal sample sizes, and I know that my larger sample, the sample that's substantially larger also has the larger variance, and then I run my statistical test and I find that my p-value is marginal, I've got a p of 0.065, Morgan, what might I claim or start to take into consideration for the fact that I didn't quite reach the goal line in terms of my test?
I was beyond spaced out, so I'm sorry.
Okay.
Repeat that for me.
Yeah. So we've got a larger, we're running a test. Our larger sample is a lot larger, also has a lot larger variance, which we know is going to produce too conservative a test, right? So I run my t-test and I find that I get a marginal effect of 0.06, right? Knowing about this, what argument might I make given that test? Anybody have an idea? What do you think, Sam?
Because the test was too conservative, I might have not reached the.
Right. However, based on these data, and these are the best we could do, we know that this test will tend to be too conservative given the unequal samples and likely the we've got kind of a large variance here, right? And so we can start to make interpretations about some of those close calls and the likely impact that might have had, right? Now, someone could come with the top of that, well, why you run it if you violated all your assumptions? So, fair enough, right? But at least you have the technical knowledge to understand what's going on in the calculation of your statistics and the types of things that might start to impact this. All right. Questions about violations, things like that? How are people feeling about all this? Reasonable? Okay. Thanks, everybody. Enjoy your evening, and let me know if you have any questions about where we're at or any of this stuff.